We will start with a presentation, an overview of textile coloration by Ali, the first hour. Then we will have a 10 minutes break, and then we will continue with the QA session. And here is your platform, the members in the chemical group. Please be active here in the chat. Ask questions and write comments. Use it as like a living document there. And we will also have a follow-up webinar. I know that some people couldn't join here today. So we will have a follow-up webinar within the chemical group, 19th of May. So just some general information. Keep your microphone muted and camera off, unfortunately. Use the chat function to ask questions or give comments. There are no stupid questions, as I say. You can also write in Swedish, because me, Mikael, and Ann-Charlotte will help here to coordinate the questions to Ali. And your comments and questions are important, so be active here, please. So the aim of this webinar is that we will get an overview, a lecture given by Ali about the textile colorations, followed by 1 hour QA session. And we choose to have 1 hour, so you will have a chance to ask your questions that is important for you in this field. And we're asking all new members and also the old members to be active here. So by that, I hand over to you, Ali. And I will stop sharing.
Okay, thank you. Good afternoon, everyone. Thank you for joining this meeting. So today I'm gonna brief you about textile coloration. So this is a crash course on textile coloration. So let me turn on the laser pointer as well as we go. So a few words about me and my background. I have background in textile chemistry and fiber science. And then in 2007, I moved to Sweden and I received my second PhD from the Division of Applied Surface Chemistry. And there I was working mostly on biodegradable surfactants. Then I was at the Institute for Color Science and Technology, responsible for environmental research group and working on colored wastewater treatment. So I have also some background knowledge about advanced oxidation for wastewater treatment. Then I joined the American University of Beirut and in the Department of Chemical Engineering. And there I was working in the domain of fiber science. Last year I joined Alto and I'm in charge of textile chemistry group here. And my research also is focused on environmentally friendly textile coloration and finishing. So the syllabus and the course that is offered here, especially this semester, I'm offering this course. So these are the topics that is covered, and I have 10 contact sessions actually for covering this course. And I should also tell you that each one of these topics, like color physics or color chemistry, is a course by itself in the textile chemistry department. So, but however, I have somehow squeezed it into like just one session for my students. And so these 10 sessions actually they have squeezed into 1 hour today. And as you can see, the table of content is quite broad. This is based on what the survey that Anna-Karin had conducted before. So I will give you a very overview of actually this course and the materials about textile coloration, and then we can move on to the question and answer session. So this is what you will see. I will give you a brief overview of textile chemistry in general, some definitions that it's very important because there are some textile terminology that you should know for understanding the phenomena. Then we will also briefly talk about natural dyes advantages, then also adsorption, and then perhaps the most important aspect of this lecture would be also the role of various chemicals. Then you'll get some knowledge about the role of each one of these chemicals in textile coloration, and if we can actually omit them or not. then we will have few slides also environmental concerns, and I'm sure that you are very interested to know more about it. So we will continue that also during the Q&A session. So general, this is textile industry. It starts from production of fibers. This can be synthetic or natural. And then these fibers, short or long, they should turn into yarn for continuation of this process. So we have a series of mechanical and physical machineries here for turning these fibers into yarn. So I have listed them here, and these are called textile technology. There we don't normally use water, but some chemicals like spin finishes and so on, they may be used. If there are synthetic fibers, or for example, if you consider man-made cellulose fibers, obviously we have solvents, we have so many other additive during the process. But normally for natural fibers like cotton and wool, the process of turning into yarn is waterless, right? So then the concern is mostly towards reducing the energy. Then we have a series of processes, as you can see here, that they are called wet processes. Of course, there we have some dry processes in between, like turning yarn into a warp, right? And then we have weaving here. This is also mechanical, but in between for adding some, for protecting the yarns against mechanical stress, then we should add some polymers to protect them. Then we should remove them after the weaving process. It contains so much oil and polymers and contamination. So before dyeing process, definitely we should remove this. So a series of chemicals, detergents, sodium hydroxide, salts, and so on, they will be used here. So maybe we will get back to this during Q&A. And then we have pre-treatment. So these are it can be for cotton, it can be mercerizing, it can be washing. Definitely most of the fabrics and that are produced, they are contaminated with various oils and waxes. They should be removed before dyeing, printing, and finishing process. And then we will have the finished fabric, and then it's a responsibility of the designer, textile designer, to design, and then it will turn into finished products. So one example is obviously textile dresses. So this is the whole process. So what we are focusing here today is actually on textile dyeing. So I will not talk about textile technology or textile finish or design. So we will just focus on textile coloration. So let's start with some definitions. So in English, they have three terms for saying color, right? In other languages, I have noticed that we are just referring to as just they have one term for referring to this colorant. So colorant is a material that is it's able to render color to other materials, to substrate, right? And it's a general word. And then it's divided into two large groups of dyes and pigments. So this is what you have heard a lot. The term dyes, as you can see, is a homophone with dye and dyeing. So don't make mistake about them. I don't know why actually this they have used this term from the beginning when it was a homophone with these words. Sometimes, I mean, if people, they don't have background textile, they will get confused with that. So however, dyes are colorants that they can render color to materials, but usually water soluble, or during the process, we can turn them into water soluble colorants. But pigments, as you can see in the definition, normally they are not water soluble, or in the media that we are using, they are not soluble, right? So this is the main difference between them. But if you refer to them as colorants, is quite okay. Then we also classify them into two large groups of natural dyes and synthetic dyes. I have one slide later. You will see for thousands of years, actually, people have used natural dyes. They have extracted with different from plants and animals and used them for dyeing process. But from 1860, the process, I mean, it was the start of synthesizing synthetic dyes. So man-made dyes started from there. We have a dyeing process. So this the idea of soaking fibers or yarns or fabrics inside a aqueous solution containing dye that it has some tendency to absorb that is called dyeing process. We have two terms here, adsorption and absorption, that I'm sure most of you are familiar with that. Adsorption normally is referring to surface, adsorption of materials on the surface. So this is the term adsorption. And if this adsorption, it's by diffusion through between the fibers and pores, and between the polymer molecules, then it's called absorption, that this is happening all the time. So both of them actually during the dyeing process, they happen. Then about fastness properties, this is another textile term that you're referring, fastness properties. So this is, by definition, is resistant against fading. So I have put two examples here. And we have various agencies. Agencies can be light, it can be washing, it can be perspiration, rubbing. So many agencies, they can work on fibers that we are using. So imagine that this sample or dyed sample has been under the sunlight. After a certain period of time, you don't see that much change, like low fading. Then this is called, in textile terminology, high fastness properties. That means that it has a high fastness and resistance against fading. The other sample, imagine again, under the same condition, you can see it has faded quite a lot. So this is a strong fading. In textile terminology, it's called low fastness properties. And this is by standard, by ISO standards, they are the value between 1 to 5. Normally, especially for wash fastness and perspiration. And for light fastness, it's a value between 1 and 8. So we can also talk about those things. So this is very important. So this is a brief history. So I told you the first synthetic dye was accidentally synthesized in the lab. Mr. Perkin was searching to make a medicine for malaria and reacted aniline with the chromate salt, and they found like this colorful material. At that time, they didn't know what was the structures. Like many years later, actually, this structure was defined, it was found. And so that was the start of, actually, it was the first synthetic dye, but it wasn't the breakthrough, right? So as you can see here, I have written that people, they have used natural dyes for dyeing natural fibers for thousands of years. So this was the start. And then the breakthrough was in 1860 by the development of azo colorants. You don't see azo, this is the azo, so nitrogen-nitrogen bond, it's referred to as azo bonds. And this reaction is azotation, deazotation it's called. So that was a breakthrough in the history of synthetic dyes. After that, millions of synthetic colorants were synthesized with the same route, but nowadays perhaps between 10,000 to 15,000 actually they reach to industrial scale, and still they are in use, right? So this is like a brief history about them. And since 1924, there was the Society of Dyers and Colorists. Actually, they started gathering and classifying all these like colorants that they were synthesized. And now the fourth generation, it was published online in 2000. And it's available online. So if you need some information about like classification and dyes, so you just search about color index and this web page, you will see this web page. Of course, you should pay a fee for finding some of this information, but it's a very valuable resource for this. So what they have done is actually, you will see on the next slide. So they have classified all these colorants that they were produced in a larger scale into two categories. One based on the chemical structures that I have listed here, right? And if you pay attention to also the values that I have reported on the percentage in the market, you will see that nearly 60 to 65% of them, they are azo structured. That was why I referred to the deazotation in 1860 as a breakthrough in the history of synthetic dyes. So whatever is available in the market, 60, 65%, they have azo structures, then 15% they have anthraquinone structures. And then you see that color index they have divided also these colorants based on their application to, and you can see acid, basic, direct, disperse. So these are like based on application. So for example, the dyes that are really good for direct coloration of cellulose without using mordants, they have named direct. Then you may not see like so much difference in the chemical structure, but whenever colorants has a substantivity, that means natural attraction towards a fiber, then it can go under the umbrella of one of these classes. So based on the results that I have seen in textbook from like 2000, and I have also listed these books, Colorants and Auxiliaries, that was published in 2000, you can see how the distribution of these classes, dye classes, are towards like the fibers. So at that time in 2000, the share in the market for cotton was around 48%. So you can see all these classes of dyes that I have listed here, direct, reactive, VAT, and sulfur, they are all mostly used for coloration of cotton. Polyester is mainly dyed with dispersed dye. So at that time it had, so the share in the market was 25% for polyester, and the share in the market for dispersed dyes was 20%. So in 2000, the total fiber production was around 50 million tons per year. And rough estimation, if you want to have estimation about how much dye is needed for textile coloration, I will tell you it's between 1 to 2% of the fiber production. So on average, let's say 1.5%, right? So if you multiply with 50 million by 1.5 or 1.6%, you will get a number around 800,000 tons. So this is the total amount of dyes that are used. What is going to happen? What I mean, the results, the statistics are for 2000, but I can tell you in the future what's going to happen based on the production line. So this is a very nice slide and information about the production of fibers generally since 1965. As you can see, the share in the market for synthetic fibers in 1960 was almost zero. They just started, producing like synthetic fibers. So the share was very low before 1965, but from there you can see that gradually there was an increase. So by increasing the population, the need for more textiles, then also the need for textile colorants increased during the years. So normally I spent nearly 10-15 minutes on this slide to explain them about what has happened during these years. But currently, this is till 2018, but roughly, what we can expect also in 2020 is that the share in the market for cotton is around 24% now, and synthetic, mainly polyester fibers, they have 64% share in the market, and man-made cellulosic fibers, they have reached to 6%. So now the total production of fibers is around 100 million tons. So since 2000, that we said that the textile colorants production was around 800,000 tons. So you can think about now it has been doubled. So the same amount, so 1.6 million tons of textile colorants now currently is used. And based on the production, you can have an estimation about the total production. So some examples, I have intentionally reduced the chemistry part of this presentation and so on, but Anna Karin told me that it would be okay to show also some chemical structures. But these are like some of the colorants that it would be extracted, for example, from madder. This is like a plant, and from the roots of this plant by extraction, what the solvent is extraction, you can get these colorants. So what you see here actually is a mixture of these colorants. More or less, it contains, so this is by chemical structure, they are anthraquinone structures, and then you see some moieties linked in different places that it gives a bit of like water solubility also to these structures, right? So some other examples like carrots. So beta carotene, so that's the main colorants of like in carrots. Then what you see here, and also in the previous example, what is giving actually the the color to this material is this conjugated system. Conjugated system means the double bond of carbon, single, double, and you see by extending this conjugated system, so they can somehow transfer electron from one side to another, so they can also have resonance. And another most important things about textile colorants is that they are they have a planar structures. That means that the whole structure that you will see actually is in one plane, right? So this is the structure. So this cloud of electrons on both sides, they can help like transfer of electron from one side to another. And that's a matter for like textile chemistry and color chemistry. Then another example here, you will see the same story here, the conjugated system. This is curcumin, and they can be used also for food, and they are eatable actually. They are colorants that they are eatable. This is one of the topics that I'm sure that we will get back to that during Q&A, but I want you just write your thoughts about advantages and shortcomings in the chat box, as I don't want to stop here. We don't have that much time, but I think this is a good thing, we will discuss, because I know many of you believe that natural dyes, they are coming back to the market, they have a future. So I would like you to write down advantages and shortcomings in the chat box, and then we will get back to these in the Q&A session to discuss about advantages and shortcomings of natural dyes. So a few words about like textile coloration by various dyes. So acid dyes, these are anionics. Why they have been called acid? Because normally, I mean, the first time that they were developed, they can absorb on wool fibers, the fibers that they have cationic dye site, dye absorption site in acidic media. And I will discuss this later, why we should use acid for dyeing process. So as you can see in the structure, they have sodium salt of sulfonate groups here, right? So when it dissociates in water, this is responsible actually for dissolving this structure that it looks hydrophobic in water. And when it dissolves in water, it has a negative charge. So that's why I have shown this with a circle with negative charge here. So you can imagine this as a negative charge. So it's anionic. That's why we call it anionic. And if we have a substrate that we can develop cationic charge on it, then the absorption can be facilitated by electrostatic interaction, so positive, negative. Of course, it's not that simple. It's much more complex, but I have simplified it as much as possible. There are many other intermolecular interactions involved. Then the same story for cationic dyes. There are some fibers, like acrylic fibers, that they have some anionic dye size at the end groups, or they have a surface charge that is negative. So for textile coloration of those fibers, fabrics, yarns, we can use cationic dye. So this is one example. It's malachite green, and you will see in this structure also the powder. So when they are dissolving water, this is also responsible for dissolving the whole structure in water. And then again, by electrostatic interaction, they can absorb. Still, there are many other intermolecular interactions that they keep these dye structure between the polymer chains. Then we have reactive dyes. These dyes were developed in 1956. So it was also a breakthrough, because many companies and customers, they were after dyes with the highest wash fastness properties. And then ICI company in England actually developed for the first time these structures. So they reacted simple acid dyes with 3-chlorotriazine, and then they produced these D-chlorotriazine. So the reactive part of this molecule, it's the one that I put on the dashed line. Right, so for the reaction to happen, so for example, let's imagine this is cellulose and we have many hydroxyl groups. So these are this chloride here in the structure. They are good living groups, right? So during the reaction, we need to activate this hydroxyl group. That can happen with sodium hydroxide. And then these will react and HCl is produced. So during the reaction, we need some other salts to be used. But the good thing is that these dye structures are chemically linked to the surface, right? That's why the wash fastness properties resistant against fading by repeated washing is very high, correct? So they are chemically bound to the surface. These are different from the previous two examples that I provided. They were with electrostatic interaction. So by a strong washing process, that may lose interaction and may migrate or desorb to the dye bath. But here, there is not such a possibility. If they are linked chemically, it's part of that molecule. So it's very difficult actually to break that bond unless with very strong chemicals, oxidating agent or reducing agent. The same structure or similar structures, they can also be used for dyeing wool and nylon fibers. So for example, for wool fibers, we have carboxylic groups and amine groups at the end of the chain. So therefore, these dyes, this class of dye can be used for the same purpose. And dispersed dyes, as this is just one example, as you can see, they don't have any group responsible for dissolving them in water, right? So therefore, lots of other material like surfactant or dispersing agent should be used to keep them dispersed in the solution. Normally, they have tendency to have large aggregates. So many of these molecules, they go together, so they are aggregating water. So we need to add dispersing agents, commonly known as surfactants, by mixing. So, and also some polymers, they can do the same. So keep them in as small particles as possible. And the dyeing process, for example, imagine if it's like a hydrophobic material like polyester, they don't normally absorb dyes like acid dyes, cotinic dyes, and so on. So they were actually developed for synthetic fibers that are hydrophobic. They don't have any tendency to absorb water, right? So the mechanism for dye absorption and diffusion inside is that we are by increasing the temperature, the gap between these hydrophobic polymer chains increases, and it gives a chance to these dye molecules to diffuse inside, right? And they will be entrapped. So mostly the mechanism for keeping these dye molecules between these polymer chains is that by diffusion at high temperature, and then there will be mechanical entrapment in between. So this is the way that they stay in there. And as polymer and dye is hydrophobic, it doesn't have any tendency to dissolve in water. When it's dyed and you're washing it repeatedly, so there is no tendency actually for these dyes to migrate to solution. So they have also very high wash fastness properties. So now we should talk about the role of various chemicals. As I told you, this is very important to understand the role of chemicals, why we are using chemicals, why so much water is used in the process. So I have picked some of these materials that may be of interest to you to explain them one by one. So this is what you will see about the acids, alkaline, metal salts, organic leavening agents, and the effect of temperature. So I will explain them briefly one by one. So before we continue, it's important to know that, for example, this is the effect of pH, right? And one example is like wool fibers. So the wool, can be symbolized with fibers. It has many end groups that they are amine groups and carboxylic groups at the same time. So the number of positive charge and negative charge at pH 5.5, they are equal. So there are equal number of positive and negative. This is called isoelectric point of wool fibers. If you add acid, like HCl and other acids, and reduce the pH, what will happen? These amine groups will be more protonated. So therefore, you will promote the number of positive charge on the fiber. That's why acid dyes that we mentioned that they have negative charge, they are dyed in acidic media. That's why they got that name acid dyes, correct? So in acidic media, they can absorb on the surface. And by changing the pH, actually, we can control how fast these dyes can absorb, correct? And the same way, if we are increasing the pH towards alkaline pH, the number of negative groups, they increase. So they can actually repel these anionic dyes by electrostatic repulsion, right? So this is a way, pH is a way to control the absorption rate, and it plays a very important role in dyeing process. The other example that I provided here for is dyeing cellulose. This is the structure of cellulose, and you know that there are many in each repeated unit. There are many hydroxyl groups present in cellulose, either man-made or cotton, right? And the dyes that are normally used for dyeing cellulose, they're called direct dyes. And as you can see, these dyes are also anionic. That means that they have negative charge, correct? So dye is negative, and normally cellulose in neutral pH, it develops a negative charge. So there is sort of electrostatic repulsion between this dye and cellulose. For enhancing the absorption and increasing the substantivity of that dye to be absorbed on cellulose and go between the fibers and diffuse in the region, so we should reduce the charge, right? And therefore, we are using sodium chloride. That's why sodium chloride, sodium sulfide is used so much in dyeing process for neutralizing, enhancing the dyeing process and exhaustion. At the same time, there is another salting out effect. That's, I don't want to go that deep, but by increasing a salt that is more soluble in water, here is sodium chloride. The other salt, that it is actually organic salt, with lower solubility will be pushed towards like a substrate. That means it will precipitate in water if there is no substrate, right? But if there is a substrate, there is a tendency that actually that dye can absorb. So these are the main reasons that we are using salt. So reducing the solubility of dyes in the water, so that will enhance the dye absorption on the substrate because there are some hydrophobic interaction between them, and also neutralization of this negative charge. So by reducing this neutralization, there is a better tendency. At least it's not a repulsion between them. Then the other most important parameter is temperature. Temperature plays a very important role. If you have aggregation of dyes, that it always happens, for many of the dyes that they have low solubility in water, they tend to aggregate, right? So opening up these aggregates, we are increasing the temperature. So if they have, for example, some groups responsible for solubilization of dyes, the solubility of ionic dyes will increase by temperature. So this is one effect that temperature has, right? So the solubility will increase, and then this with a smaller molecular size, they can diffuse better. The other role is that, imagine these are like polymer chains. It can be for cellulose. Here I have written cellulose, but it can be any fibers, right? And they are tightly packed at room temperature. And that's something also regarding the glass transition of that polymer. That's why some of the fibers like polyester, they have very high glass transition. That means that you should go increase the temperature above 100, 120 until this structure will open up and let the dye molecules to penetrate and diffuse inside. So the second role of temperature is to let these fibers and molecular chains to open up a bit. These molecules that they are in a nanometric scale, even smaller, they will penetrate between these molecular chains. And then by reducing temperature, they will be entrapped. And there are many like intermolecular interaction between the dyes and polymer chains. It can be electrostatic interaction. It can be hydrophobic interaction, and so many others. So this is the role of temperature. So it will enhance the dyeing process. And also, as you can see here, by increasing temperature, we said that they are also increasing the solubility. So if they are adsorbed on one place with high concentration, on the other place that with lower concentration, that means that we have uneven dye adsorption, or we call it non-level dyeing process. So by increasing the temperature and prolonging the dye process, there is a chance that these dyes that are adsorbed again go back to the water and again adsorb on other parts, right? So this way you can enhance the distribution of dyes evenly on all parts of the textile goods, fiber, yarn, fabrics. Then it's about the water. So this effect, the term that we are using in textile terminology is liqueur ratio. Normally, perhaps you will see this as L to R ratio again, but that's very simple. That means how much water you're going to use during the dyeing process. So with this example here, when you are increasing the L to R ratio, that means that for the same condition, for the same dyeing, you are increasing the amount of water in the dye bath. What will happen? What with results that when you have more water, it's a solvent, so it can dissolve these dyes better, correct? And then uniformity of the distribution as absorption will increase. But it has a bad side that, first of all, I mean, more wastewater will be produced at the end, right? So we don't want to increase L to R to the very large values. And the other thing is that we should keep the textile inside the solvent, right? It should be always covered. So if L to R is very low, that means part of this material is, for example, out of this solution. That will cause that, for example, one part of the material will absorb dyes, but the other part is outside of the solution. So definitely we should optimize this in a way that the whole material should be in the dye bath for the dyeing process to happen. What dictates this? Also the textile machinery. We will get back to this during the Q&A session to see that machines that they have developed or they have different L to R ratios. But the effect that it will cause for the dyeing process, I have listed some of these, right? So consumption of water and steam is obvious. By increasing, you have more water, you need more energy also for heating up that solvent and the dyeing bath. Dye exhaustion actually will decrease because you are solubilizing more dye in the dye bath. So the chance for absorption would be less. Uniformity will enhance definitely because you have soluble, you have more solvent, but the consumption of dye almost remains the same. So you have the same, I mean, a species there, right? So that L to R doesn't change anything. You want to, for example, dye 1 kilo of fiber, then you need 1% dye. So that will not change. It doesn't matter how much water you're adding. Effect of alkaline pH. So this is similar to what we discussed about like wool fibers and effect of, but here you see that cellulose can be actually ionated by adding alkaline, a strong alkaline, sodium hydroxide. So we said that it has a slightly negative charge, right? For some dyeing process, it's needed actually to enhance this like negative charge. Then therefore, for example, for cellulose, you add sodium hydroxide. If you do the same to wool, you dissolve wool. I mean, you will destruct it because the chemical structure of wool fibers cannot tolerate sodium hydroxide to high concentration. But cellulose is quite fine with sodium hydroxide. On contrary, cellulose cannot tolerate addition of acids, right, like HCl. So as a result, you will ionate. So this is called cellulosate ion, right, by adding sodium hydroxide. Why is it important? Especially for reactive dyeing, we should add sodium hydroxide to actually activate those hydroxyl groups for adsorption of reactive dyes. So this slide shows the cellulose dyeing with reactive dye. So I have symbolized cellulose here with ClO- and Na+, right? So that means that we have activated some of these hydroxyl groups here. And I have shown here the reactive dye with the dye and the CCl. CCl is the reactive part of this dye. So what will happen when we are reactive, adding like sodium hydroxide, so this will be activated. The dye can react chemically with the structure, with the cellulose hydroxyl groups. As a result, Cl from here and H or Na, that here we had Na, will be released on, correct? So chemically, is bound to the cellulose and sodium chloride is produced. I'm giving this example because I want to show you a recipe and then you see how much salts are used for during the dyeing process. You may be surprised. The bad things or shortcoming of reactive dyeing is that water that is a solvent there, it has also hydroxyl group, you see? And also sodium hydroxide, also it has a hydroxyl group there. So the dye molecules, reactive dye, can the same way react with water molecules. They can react with sodium hydroxide. This is called dye hydrolysis. That means dye will be wasted to water. Instead of reacting with cellulose to be permanently fixed by chemical bond on cellulose, it will be wasted to dye bath. And that generates something between 5 to 50% of the initial dye concentration remains with 30 to 50 grams per liters of salt and sodium hydroxide. That's quite high concentration of like pollutants in water. So this is Diagraph. This is called Diagraph. So whenever you're dealing with textile dyeing and then you're buying, for example, certain dye from a company, then they will provide you with a graph, right? So here, this is a general, just one example. I want to show you how it looks like for dyeing. So imagine that this is the dyeing process for the reactive. So cellulose or cotton is going to be dyed with reactive dyes with different types. So I have written different reactivity, right? So it doesn't matter. That's something that it will be dictated by actually the supplier. It will tell you that you should increase the dyeing temperature is 80 to 90. That means this T value here, the maximum temperature, it should be like 90. If the reactivity is really high, you don't need to increase the temperature to that. So 25 to 40 is enough. So normally the water is added to machine. The textile goods is there, right? For like 5 minutes it stays, or like it will be circulated without adding any chemicals. Maybe 2-3 minutes, 5 minutes later, they are adding the salts that is needed. So sodium chloride normally is added, right? Again, it's circulated, so they will give some time actually for the whole goods to pick up the salts and then neutralize also the charge. Then here they're adding dye, right? That can be added gradually. It's low because especially for reactive dyes, there is possibility that the absorption will start even at low temperature, correct? So that's, I have put just one arrow here, but there is possibility that can be added gradually during the time. So it stays there, and then based on the recipe that we have here, we should slightly 1 degree or 2 degrees per centigrade, we increase the temperature to that set temperature that we are provided here based on the dye class. So we continue until dye is absorbed, right? And during this process, maybe 30 minutes, 40 minutes later, now we are adding sodium hydroxide. Now you know the role of sodium hydroxide, right? This is for activation of cellulose groups to now be chemically linked. They are not adding this in the beginning because they don't want the fixation to happen because there is a chance of unlevelness, non-uniform distribution and absorption. So they are adding when partially dye has been absorbed by different mechanism. Now they're fixing it in place by adding sodium hydroxide, correct? And then they follow the washing process. So let's see how much chemicals are used there. So consider this scenario for this example, that we are gonna dye 100 kilos of cotton. It can be any form with 3% reactive dye. And now you know about L to R ratio. So I will explain how you calculate 1 to 30. So you're asked, for example, dyer is asked to calculate the amount of chemicals that they are needed for this dyeing process. So water for dyeing is 30. Where did I find this 30? Is L to R ratio. That means for 1 kilo, I need 30 liters, right? For 100 kilos, it will be multiplied by 30. So I need 3,000 liters of water if L to R ratio is 1 to 30. This is quite common for winch dyeing or basket dyeing. This is the L to R ratio. We have dyeing machinery with L to R 1 to 1 ratio, right? So that has been, we will discuss it later. But normally in the lab or if the sample, this is the amount of water you need for dyeing process. Then the amount of dye that is needed, 100 kilos times 3%. This is the 2% that you were asked to. So you will multiply it. So you need 3 kilos of dye. And that's the most expensive chemical that you need for the dyeing process, right? Then sodium chloride is normally 40 grams per liter. So multiply by this 3,000 that we obtained here. So you will need around 120 kilograms of salt. Is huge. For 100 kilos, we need like 100 kilos of salt, right? And what will happen? It will stay in the wastewater. So it will be discharged. And then sodium carbonate, this is like for activation of those hydroxyl groups. So it needs 5 grams per liter. So again, 15 kilograms of sodium carbonate. So most of these chemicals, they remain. And we said that also part of these initial dye concentration, up to 20-30% of these 3 kilos of reactive dye also remains in the wastewater. So it's good, I've just copy-pasted that calculation table here to just see what we have here. So you may ask how much water is required in total. The total water is much more than these 3,000 liters that you will see. Before dyeing, we should wash cotton. After dyeing, we should definitely wash. And that accounts for double the amount that you will see here. So 10,000 more, right, of liters of water is needed for the whole process for that 100 kilo. How much dye will remain in the dye bath? I told you that, especially for reactive dyes, the adsorption is not 100%. So you can assume 20% remains. So let's say 600 grams of this dye will remain in the wastewater. How much energy is required? That depends to the dyeing machine and how long we are keeping that, and also the temperature of the dyeing process. So I will not give any value, but there are some values reported in the literature. And then I don't think I need to answer this. The environmental concerns are all about these, like remaining dye and how much salt we have used during the process and what it remains in the wastewater. So these are all environmental concerns. So few words about textile water consumption. So I have prepared this slide especially to highlight how much water is used in this industry. And of course, that's also from one of the web pages that I found. China by itself is responsible for production of let's say 50% of textile clothing. And for that, they are using around 2.5 billion tons of water, and then that will turn into wastewater. So for production of a pair of jeans, let's just consider this. For producing 1 kilo of cotton, we need around let's say 10,000 liters of water, right? So a pair of jeans is 300 grams. And the dyeing process, it needs also around 2,000, 3,000 liters of water for dyeing, washing process. So roughly for production of 1 pair of jeans, we need around 8,000 liters of water. Just imagine. That equals to 40,000 glasses of water. That can keep someone alive for 10 years. So this is the environmental concern. It's not just about the chemicals that remain in wastewater. That can be treated, of course, but the water consumption is really high in this industry. Then about other environmental concerns here, this is the table showing that how much dye will be fixed on the fibers. And also here you can see the corresponding dye class with the fiber. For example, I told you that acid and metal complex dyes are normally used for wool, dyeing wool, and nylon seal, right? So normally wool, it absorbs dyes very well. And also nylon. The dye sites are many, so up to 98% absorption can happen. So you may end up with wastewater without any dye, actually. So this is a good thing about it. The same thing about the acrylic dyeing. These are mostly the polymers that we are wearing in winter time. Normally they are dyed with basic or cationic dyes. Again, the absorption rate can be really high, 95 to 100%. So the remaining dye can be between 0 to 5%. Dispersed dyes is the same, so we can reach to 90 to 100%, but for cellulose, it would be a disaster. So all these classes of dyes, direct, reactive, sulfur, VAT, so these are the classes of dyes that you're normally using for cellulose, and it has nearly 40% share in the market. And you can see the fixation is very low because cotton actually doesn't have good dye sites. That's the issue. And then you can see the remaining dye in the wastewater for cotton and cellulosic generally is really high, 5 to 30%, 10 to 50% for reactive dyes, which is very high. And as I told you, so generally 20, 30% of the initial dye concentration remains. It will be hydrolyzed. Sulfur dyes now, they have been banned, but still in Asia, they are used. So 10 to 40%, and also VAT dyes that they are used for dyeing denim. So roughly, to see the environmental issues, also I prepared this slide to show you that many other chemicals are obviously they're used. CO2 of the wastewater, this is chemical oxygen demand, right? So how much oxygen is needed to destruct, for example, the chemicals in the wastewater. So do you see this is the really high. And I've seen also some reports that's showing between 10,000 to 15,000. So that depends to the what type of material is dyed, what type of dye is used, and so on. BO2 is normally for dyeing process is not that high, but here, as you can see again, for this textile mill, it has been reported to be really high. So these are really high values, and also total solid content, solubilized solid, and you can see these are all very high values. So these are like all concerns that we can later on get back to that and discuss. Let me see how much time I have. So we have another 10 minutes. Then you may also be interested to know about the aquatic toxicity of these colorants. So I've found some scientific papers that they had reported also aquatic toxicity. The interesting thing about aquatic toxicity of these colorants, that here, for example, in this report, that this table is from this handbook of environmental chemistry. So these are their somehow results that they have gathered from many companies that they were producing dyes. And the report is, as you can see, it's very old, 1980. So that's most probably between the last 10 years, from 1970 to 1980s, they have gathered all this information. So out of 3,000 commercial dyes that they have tested on fish, the aquatic toxicity of just 3% are really high toxic. That means the value, LC50 value, lethal concentration value, less than 10 milligram per liter. And for 97%, actually, they have found that out of these 3,000, they have low toxicity, correct? So obviously, these are issue, even 2% out of 3,000, there are quite many, right? So, but however, generally, they are not that toxic to environment. And the other fact is that you should remember that some of these dyes, I mean, they are discharged this concentration around 10 to 100 milligram per liter, but there are many other wastewater that they will be mixed with them. So they will be diluted even to around maybe 1 or less than 10. So generally, textile wastewater, although you will see they are very colorful, even 1 ppm can be seen, but that concentration normally is not that toxic. Of course, I mean, it has a certain toxicity. It's a low level of toxicity, but this is what I found. Then there is another report on oral administration of colorants to mice. And here they have tested 4,661 commercial colorants. Again, the same story. Even by oral administration, you can see that 90% of these dyes, they have toxicity. Low toxicity, that means that they are above 2,000 milligram per kilogram, right? So therefore, they're not considered. And I should also comment here about this percentage. What are these? I mean, what classes of dyes? So from all classes, they have been found that there are some in this category. And mostly the dye structures that they have some halogenated, like chloride or fluoride, bromide. Those are, and the one that they also have some metal complex. So they can be found in this category, but you can also find some of them that they are not that toxic. So this is something that we can get back to that and discuss. And this is final slide for presentation. And so I wanted also to brief you about the printing, because there were some questions and concerns about the printing process and also the chemicals that they are used. So I will briefly tell you about the chemicals that they are using in the printing process. This is it's a course by itself, but and we have actually textile printing course that we deal with that. But just to give you a brief overview of what is happening, very similar to paint that we are using for painting walls and so on. So there are some formulation that we can actually have, print or transfer colorants on fabrics, right? But here there is a big difference between what we're using like in paint, because that makes a very hard film. But here you are after something that is flexible, because textiles are flexible and we want them to stay flexible even after printing. So the idea is that we have some like colorants, I'm referring to as colorants. So dye and pigments, both they can be used, and pigments are now picking up because the addition and the formulation it would be much easier. And what I have also listed here, this is one example of adding pigment reality, but dyes can also be used. So the idea is that we will formulate this. We should first of all have a paste, right? It shouldn't be watery like what we have in the dye bath. Otherwise, it will splash, it can penetrate, and then it doesn't accumulate on the surface. The idea is that we will just have these colorants on one side or the top surface of the fabric, correct? Then, so these are the colorants, the red ones. Then we have some binders. So these are, they can be some monomers that upon like solvent evaporation, they can actually start polymerizing, turning into a film. Right, so I have shown them with these diamonds, blue diamonds, that after fixing, curing at high temperature, when solvent evaporates, then they will make like some sort of film that they are clear films, right? So the responsibility of the binder is to keep the dye on the surface, so with the film. If we are using pigments, there is no tendency for pigments to penetrate or absorb by fabrics, right? So it remains on the top surface. So that's the downside or shortcoming of textile printing. That means that the rub fastness, if you're rubbing the surface with other, so there's possibility that gradually these pigments then can leave the surface. And the other is that these film, that they are flexible, after like repeated washing, they may have some cracks and they will lose their strength and they will leave. Look at the printing paste recipe here. So you can see they have used 10% water, 60% oil, which can be white spread. So what you can see is like much more concentrated than what you see in the dyeing process, right? And what you should know is that in this process, during the fixing, curing, all these will evaporate. So 10, 60, around 70% of like that solvent and water that they are mixed together with a surfactant or emulsifier, they will evaporate. And we will end up with just pigments, thickener, binder, and catalyst. That they should be also part of this, they should be go away. So the only thing that it remains is the pigment and the binder that it will remain, and the rest should be washed off. After printing, we should also wash it off, correct? So, and the reason why we are using emulsifier here is that we have a mixture of water and oil. They are not miscible, so we should have a droplets of water in oil to be well dispersed and emulsified. And the thickener is responsible. These are some polymers that we are adding to formulation to increase the viscosity. As I told you, we need like a paste, so it should have certain viscosity in order to be able to like transfer them on the surface. Okay, so with this, I will end this presentation, and these are some of the references for the photos and like materials that I've got from here and there. So I left it here for you. Now, I think we will have like 10 minutes break, and then we can start the question and answer. But I encourage you also, if you have any question about here, we will follow some of these again. We can discuss this. But as Anna Karin mentioned, that for having a fruitful discussion, it would be better to write down your question in the chat in Swedish or English, fine, because Anna Karin will moderate the session, and she can translate even if it's in Swedish. Thank you so much for listening.
Thank you, Ali. Thank you very much for a comprehensive and pedagogic presentation. So let's take 10 minutes break, and please write your questions in the chat. And I really encourage you to be active here. Any questions relating both to chemicals, quality. I know we have product developer here also.